We'll continue our discussion of blade flapping dynamics. We developed this equation for the blade flapping up and down. Beta is the flapping motion as a function of time. These are the angular moment. This is the moment generated at the hinge by aerodynamic forces. This is the moment generated at the hinge by inertial forces. This is the moment generated by the hinge by centrifugal forces. So all the three have to balance, so they come up as this situation. We said this looks like a spring mass system. So this is like a m times x double dot plus k times x equal to 0 if you neglect the right-hand force term. The natural frequency of the spring mass system is square root of spring constant k over m. So spring's constant is I omega squared over I. Square root of it is omega. So the blade has got a natural frequency of omega. So left itself, the blade has a tendency to flap one time up, one time down, one per rev. It'll go up, come down. So this is the natural frequency of the system. Now let's look at what happens if you submit a resonance force here. This is that model problem. There's no damping in here. So this will, if you don't have a damping term, this will become infinity very, very quickly. So to avoid that, we add an artificial damping term here, just to illustrate this, how the equation behaves. In a real world, we don't have an artificial damping at the hinge or a mechanical damping at the hinge. The aerodynamic itself provides the required damping. Okay? So it's got a beta dot term somewhere buried in here, which we will develop later on. Therefore, it provides adequate damping by itself. But here we are saying there's a damping. This is the system. This is my force. So I'm going to apply a force at the natural frequency of the system, at the resonant frequency. So where it says sine of omega t. We want to solve it. So from our ODE classes that you may have taken, what you do is you assume a solution, plug it on the left side, because beta appears on the left side. Take two derivatives with respect to time, single derivative with respect to time, no derivative, just plug this in here. Then you're going to get a sine terms, cosine terms, equate the sine terms to sine terms, there's only one. Equate the cosine term on the left side to cosine term on the right, there's none. Then you can get two equations and you can solve for the B and C. Okay? This is called the harmonic balance approach. So when you do that, it can be easily shown that the beta equal to this amplitude that you got, forcing amplitude, divided by this damping constant C times the natural frequency omega in radian per second times cosine of omega t with the minus sign here. So this minus sign can be written as sine of omega t minus pi over 2. Okay? So yeah, this is the expression that you would get. So force varies as sine of omega t. The response is taking place 90 degrees later. So in a resonant system, if you apply a actuation motion, for example, let's say you apply a 1 degree rotation to the blade at pilot's right, the lift immediately goes up to the pilot's right, because you have produced a change, instantaneous change in the angle of attack. But the blade does not flap up instantaneously. It takes place 90 degrees later in front of the pilot. Same way, if you decrease the angle of attack by 1 degree on the pilot's right, the lift drops, but the blade does not immediately droop. Because of its dynamics, it drops in front of the pilot. So this is how you control the swash plate. By swash plate, you're changing the blade pitch angle, then that translates into the tip path plane orientation. So this is very simply the blade response to pilot input. It looks complicated. You have to review this many times, perhaps look at some videos, YouTube and so forth to get some idea of what's going on. So what happens when the pilot is tilting the short blade back? The rod in front of the pilot goes up. It's mechanically connected to the pilot's blade on the pilot's right, so that blade will pitch up instantaneously. So the lift will go up. Then 90 degrees later, the blade will flap up in front of the pilot. So if you do this at 90 degrees, the response will be at 180 degrees. How about the other blade that would have pitched down at 270 degrees? Then the response will be the blade will flap down behind the pilot. So what you have done is you have moved the tip of the blade, one in front of the pilot up, behind the pilot you have down. So you have tilted the tip pad plane. So you have tilted the thrust vector. So now you have generated a rearward directed thrust. So one part of it is holding up the weight, vertical component, but the rearward component is not overcoming the drag, it is adding to the drag, therefore it's slowing down the vehicle. So this is what you would do when you want to land on top of a building, or when you want to land in a clearance, you would see the rotor tilts the disc backwards. How did the disc tilt backwards? The pilot moved the control rods, autopilot or the pilot's control, tilted the Schwarz plate so that the front part of the Schwarz plate comes up, the rear part of the plate comes down. The blade to the pilot's right pitches up. That blade moves up in front of the pilot 90 degrees later. So you see the blade is up here. The other blade is flapped down. So this is what has happened. So the pilot is doing his actions on the Schwarz plate level here, which we call it a no feathering plane, but the blade response is taking place here. By the way, this angle is not same as this angle. These two lines are not parallel to each other. They're inclined at an angle that we will develop later in this video. What happens if the pilot tilts the Schwarz plate to the left or right? So let's say that the pilot switches the throttle plate to the left. Then the push-pull rod to the pilot's right will come down. Above the rotor disc, I should say, in the Schwarz plate, it will come down above the pilot's head. Then the blade behind the pilot will pitch down. Alpha has decreased, lift has instantaneously decreased, but the blade response will take place 90 degrees later, so the blade tip will come down to the pilot's right. Same thing, the opposite will happen to the blade to the pilot's left, it will come up, so you have tilted the tip pad plane sideways, so you have tilted the thrust vector sideways, so now we are producing a sideward directed force which will cause the vehicle to side slip. In reality, what would happen is this force is going this way, the weight is going straight down this way, so it will produce a rolling moment, so the fuselage will also rotate, so the whole vehicle will bank in this direction. So that's what would happen. So pilot controls the Schwarz plate, which moves the pitch link up and down, which changes the angle of attack, which changes the forcing function, but the response takes place 90 degrees later. So this is how the blade flapping dynamics works and how the pilot is able to control which way the thrust is pointing. Whether it's a physical pilot or an autopilot, the principle is the same. Now we are coming back to our original equation. So we are going to try to get a flapping dynamic solution. So what we would do is we'll assume a harmonic balance approach. Instead of solving this numerically, ODE, that can be done. Some of the comprehensive codes I mentioned to you would do numerically, but they would also have an harmonic balance as a choice. Harmonic balance simply means you assume a solution of some form, throw it on the left side, analytically take a derivatives, and then find the cosine terms, sine terms, cosine 2 psi, sine 2 psi, and so forth. Equate it to what you find on the right side, term to term. So cosine term on the left side will be balanced with cosine term on the left side. Sine term will be balanced with the sine term, and so forth. This is called harmonic balance. We are going to do this in a later module after we have developed an analytical expression for CL. We are not there yet. So let's just look at what is the angle between the tip pad plane and the shaft plane, which we also call the no feathering plane or sometimes called the control plane in some books. Okay. So we already saw that the tip path plane makes an angle of beta 1c with respect to the shaft axis. So this is the angle between the shaft plane, tip path plane is beta 1c. We saw this later in a previous video. How about the laterally beta 1s? Okay, this is the shaft plane laterally running to the pilot's right y-axis. This angle is beta 1s. Viewed from the back of the pilot, looking at the helicopter, this is beta 1s. Now, pilot is inputting theta naught, theta 1c, theta 1s. If he moves all the control rods up, all of them at the same time, all the blades will pitch up collectively. On the other hand, if the Schwarz plate is tilted one way or the other, one rod will go up, other rod will go down, producing a cyclical input, as we saw earlier. So this is the pilot's input. So this is taking place in the Schwarz plate plane. So it's taking place in the Schwarz plate plane. So for example, when the pilot wants to pitch the right side blade by amount theta 1s sine psi, what the pilot is doing is he is tilting this Schwarz plate this way by theta 1s. So this goes up, then the pitch link causes the blade to rotate by that amount, theta 1s. Right? So this angle is theta 1s, angle between the shaft Schwarz plate and the shaft plane is theta 1s. Okay. And the tip path plane is making an angle beta 1c, okay, with the shaft plane. So if you put them together, one of them has got a theta 1c, the other one has got a beta 1s, okay, in the laterally viewing there. Now, if you look at the relative angle, total angle between the tip path plane, which is this dotted line, and the Schwarz plate plane, or the no feathering plane, which is this dotted line, it's the sum of this angle theta 1s, because this line is parallel to this line. So this angle is theta 1s, just like this is theta 1s. This is beta 1c. So the total included angle is theta 1s plus beta 1c. So the included angle between the no feathering plane and the tip path plane viewed from the pilot's right side, from the pilot's left side, looking at the helicopter towards the pilot from the left side of the helicopter, the angle is theta 1s plus beta 1c. It's independent of the coordinate system in which these angles are measured, because we are talking about the included angle. Doesn't matter whether we measured it with reference to this dotted line, in which case beta 1c is 0, there's no flapping, or this dotted line, in which case theta 1 is 0, there's no feathering, or about this black line, which is the shaft plane. Doesn't matter, the included angle is together is a constant. Same way, laterally, this is theta 1c, this is beta 1s. So the difference between theta 1c and beta 1s, this is included angle between the no feathering plane, which is the Schwarz plate plane, and the tip path plane is theta 1c minus beta 1s, is independent of whether you measure these angles in the tip path plane or in the shaft plane or in the no feathering plane. So the moral of the story is these combinations always occur together. The no feathering plane, you think there's no pitching up and down of the blade, so you only see the flapping dynamics. In the tip path plane, you don't see any flapping up and down of the blade, so you only see the feathering dynamics. In the shaft plane, you see both of those terms. So in our later work, we're going to see all of these terms appear together when we do the aerodynamic loading, CL. CL is function of alpha. When we try to analytically estimate alpha, we will see these things together. That means a given alpha can be generated either by flapping the blade or pitching the blade or any combination thereof. Indeed, 1 degree of pitch it produces the same effect as 1 degree of flap. Okay, so this is an equivalency between the pitch and flap. But these things we will see appearing together in our next module, where we look at the aerodynamic loading on the blades. So we will stop at this point.